We are discussing the Dirac equation, which is another way of describing a relativistic quantum particle. So, we said for a free particle, we could consider the equation I gamma mu dou mu minus m, where m is the mass of the particle and acting on psi equal to 0, where psi represents the wave function. It represents the particle and it is the wave function of the particle. Gamma mu are objects which anti-commute, which means if we take gamma mu, gamma nu with two different indices, gamma nu, gamma mu added to that will be equal to 0 if mu is not equal to nu and equal to 1 if when mu is equal to 1, that is gamma mu square is equal to 1 and gamma mu square plus gamma mu square will then be equal to 2. So, together for any mu and any nu we can write this, and gamma 0 dagger, the Hermitian conjugate, is equal to gamma 0. We have seen that actually gamma can be written in terms of gamma 0 can be is equal to beta. You remember our original form of the Dirac equation in terms of beta and gamma, and gamma I is beta alpha I, where I now runs from 1 to 3. So, gamma I square gamma I dagger, the Hermitian conjugate, is beta alpha I dagger, which is equal to alpha I dagger beta dagger, which is equal to alpha I beta, because alpha and beta are Hermitian coefficients are Hermitian, then the Hermitian conjugate of each other, and then this, because of the anti-commuting property of alpha and beta, can be written as minus beta alpha I, which is nothing but minus gamma I. So, and this says that gamma 0 is Hermitian and gamma I, where when you take the spatial components I equal to 1, 2, 3, then that is anti-Hermitian. So, this is what we discussed yesterday, and now let us go ahead and then see further what else we want to understand here. If you take gamma, the Dirac equation I gamma mu dou mu m psi equal to 0, multiply it with gamma nu dou nu, the operator, where nu is summed over, and in Dirac equation mu is summed over, gamma mu dou mu minus m psi equal to 0. What do we get? First it is gamma, well I could write it as gamma nu the other way around also. So, I have gamma nu I gamma nu gamma mu dou nu dou mu. By the way, gamma nu gamma mu are the matrices. One way of representing them is matrices, or they do not commute with each other. So, when you take one across the other, you will have to be careful. Whereas, the operator, differential operator, has nothing to do with these. So, these gammas are basically some constants as far as the derivative operator is concerned, and then they will can be easily taken across them without worrying about any other issues. So, that is what we have here. This is the first term, and then the second term is m gamma nu dou nu psi equal to 0. First, let us look at the second term. Gamma nu dou nu psi, because of the Dirac equation, is now minus I m psi, right. So, this whole thing is minus I m psi because of the Dirac equation, the first line on this slide. Okay. And therefore, what we have, so and the second one what I will do is to write it as gamma nu gamma mu plus gamma nu gamma mu gamma nu. I added gamma mu gamma nu to it. So, I have to subtract the same thing, but then what I will do is I will take half of this and take half of gamma mu gamma nu along with minus gamma mu gamma nu and half of this. Together they sum over to gamma mu nu gamma mu. First term, the third term will give you gamma nu gamma mu, and second term and fourth term cancel each other, and then we have a dou mu this thing acting on psi, and you have plus I m square psi equal to 0. So, the first term, let us look at the first term. It has two parts. One is symmetric under the exchange of mu nu. If you take the first term gamma nu gamma mu plus gamma mu gamma nu, that is symmetric under the exchange of mu and nu. If I change mu to nu, the first term becomes second term and second term becomes first term. Whereas, the second part in the bracket here, gamma nu gamma mu minus gamma mu gamma nu is antisymmetric under the exchange of mu and nu. If I change mu to nu, the first term becomes the second term, but there is a minus sign there. So, second term becomes the first term and there is without a minus sign. So, this will pick up an overall minus sign when I change mu to nu and nu to mu. So, that is why we call it an antisymmetric under the it is antisymmetric under exchange of mu and exchange of the indices. So, let us look at that antisymmetric part, gamma nu gamma mu gamma mu gamma nu, and there is a dou nu dou mu on this thing. Dou mu dou nu is actually symmetric. This is basically differential operation, and it does not matter whether if you take say nu equal to 0 and mu equal to 1, you will get differential operator dou by dou t and dou by dou x. It is the same as writing dou by dou x first and then dou by dou t after that. So, this is like interchanging mu and nu. So, therefore, dou nu dou mu is symmetric, or let me actually write it as equal to dou mu dou nu. It is the same object. So, let us look at this acting on psi. So, this first one is gamma nu gamma mu dou nu dou mu psi minus second part is gamma mu gamma nu dou nu dou mu psi. I have not done anything, just expanded it. Now, let me leave the first term as it is, but interchange mu and nu. This interchange is actually changing this to the dummy indices. or first let me change the leave mu and nu as it is, but since we have dou mu nu equal to dou nu mu, I can write this as dou mu dou nu psi. Okay. Now, this is exactly the same in the exactly the same form as the first term. If it is confusing to you because of mu nu, let me actually do the following. Let me change it to some rho and sigma, rho and sigma. Because it is a dummy index summed over independent of the other terms, I can just change it into anything as I like. Now, I can, instead of writing the first term is as it is, instead of writing changing the rho to mu, or I can change again rho to nu, which I am which I can do, and sigma to mu. So, consistently I have to do all the rhos to nu and all the mu's to sigmas to mu. Now, this is exactly like the first term. Well, you could have done it just by observing the second line here and then come to the last conclusion, but we have done it in steps so that it is not confusing to us. So, this is now first and second terms are exactly the same, therefore, equal to 0. So, in this expression here, the Dirac equation operated on by gamma nu dou nu, or we have I gamma nu gamma mu plus gamma mu gamma nu over 2 dou nu dou mu psi plus I m square psi equal to 0 is what we have. The other term is identically equal to 0. But now, we had an anti-commutation relation between gamma matrices, and that tells us that it is equal to 2 g mu nu over 2 dou nu dou mu psi e plus I m square psi equal to 0. I is common, I will take that away. 2 from the first term cancels with 2 in the denominator of that term. G mu nu will raise the index of dou nu to mu. So, I have a dou mu psi plus m square psi equal to 0. It is still a matrix equation. Okay. So, this actually says that each component of psi satisfies this equation, right. There is no other thing. So, here basically let me also write down then the Dirac matrix symbol. So, each of this is A B psi B A. This is what the component wise form of the Dirac equation multiplied by dou nu gamma mu. And when it comes to the next line, it is again A B, but G mu nu is a constant as far as the Dirac matrixing is concerned. So, when you actually write, let us go back to that. When you actually write this expression here, the anti-commutation relation, okay, we have a 4 by 4 unit matrix on the right hand side, which is understood. Since we, if you get confused, you please write that each time there. It is similar to having an unit matrix of 4 by 4 unit matrix in M. So that you can add the first two terms, these two terms in the Dirac equation. You cannot add some two different quantities. So gamma mu is a matrix, 4 by 4 matrix. Therefore, what you can add to it is a 4 by 4 matrix. So where is that 4 by 4 matrix in the second term? It's actually M times unit matrix. That's what you have. Okay. Similarly here, in the second line in the anti-commutation relation also, it is exactly the same thing that you have. Okay. Let me highlight that. Now, let us go to our this equation what we have here. So, this essentially is A and A. The wave function now has 4 components, and each component satisfy this equation, and I believe you know this equation. This is the Klein-Gordon equation, which each component of the wave the psi satisfy, right. So, that is not surprising, because we need A square E square equal to P square plus M square, which is a result of special theory of relativity, the energy momentum relation that will be satisfied by anything. So, this is another thing that we can see. Okay, and now let us come back to the Dirac equation. In the case of Klein-Gordon equation, the wave functions that satisfied the Klein-Gordon equation, we had a continuity relation written in terms of a conserved current, okay, a current whose 4 divergence vanished, that we could get looking at, or we could construct that from the wave function phi that satisfied the Klein-Gordon equation. What we did in that case is, so continuity equation, how we did that is the following way. The box square phi plus m square phi equal to 0 is the Klein-Gordon equation for the wave function phi, and then we took the complex conjugate of that, which essentially told us that the phi star also satisfies the same Klein-Gordon equation, and this led to J mu, which we could write as 2 components, rho and j, where rho is equal to I e phi star dou phi over dou t minus phi dou by dou t of phi star, and j is nothing but minus I e phi star grad phi minus phi grad phi star. And with this we had dou mu j mu equal to 0, and that in terms of the components is dou by dou t of rho plus divergence of j equal to 0, which is basically the continuity equation. Let us do a similar thing for the Dirac equation. So, what we have is gamma mu dou mu minus m psi equal to 0. take the complex conjugate of that, or let me first write it in terms of the time and the spatial components separately. Dou by dou t of psi gamma 0 plus I gamma j dou psi by dou x j minus m psi equal to 0. Take the complex conjugate of that will give you minus I. Actually here, because we are dealing with a matrix equation, we have to take the Hermitian conjugate. Okay? So, let me write that for you. Let us take the Hermitian conjugate of the equation. I will be equal to minus I, A, B. If two matrices are there, the Hermitian conjugate is basically B dagger, A dagger. The Hermitian conjugate of B first and then the Hermitian conjugate of A. This is because there is a transpose of the matrix involved apart from the complex conjugation in Hermitian conjugate. Minus, so this Dirac equation will give you minus dou by dou t of psi dagger. The complex conjugation or the transpose will not affect dou by dou t. So, it is actually psi dagger that will be affected, psi that will be affected, and then the second one is gamma 0. So, gamma 0 dagger minus I similar way dou x j psi dagger gamma j dagger minus m psi dagger equal to 0. We know what gamma 0 dagger is, it is gamma 0 itself. So, we have minus I dou by dou t psi dagger gamma 0, but gamma j dagger is minus gamma j. So, there is a change of sign there, it is plus I dou by dou x j psi dagger gamma j minus m psi dagger which is equal to 0. So, this is now a little difficult situation here, because the will not really be able to write it in a covariant fashion. For that is because this is now minus I dou by dou t of psi dagger gamma 0 minus dou by dou t dou x j of psi dagger gamma j. Instead of a plus, it is a minus relative to the 0th and the spatial components. The way out is to multiply it by a gamma 0 from the right. When I multiply by gamma 0, this will give me minus I dou by dou t psi dagger gamma 0, another gamma 0, minus dou psi dagger x j gamma j gamma 0 minus m psi dagger gamma 0. So, everywhere I multiply by a gamma 0 from the right side and define psi bar as gamma dagger psi 0. This will give me minus I, first term I will club psi dagger and gamma 0. In that will give me psi bar, but the second term I have to switch gamma j and gamma 0. When I switch gamma j and gamma 0 and write it as gamma 0 gamma j gamma 0 is gamma 0 gamma j with a minus sign. So, there is a switch of sign again. So, that is what we will make use of. So, that will give me dou by dou t of psi bar, and there is a gamma 0 which is left out, minus, in this case I have to switch this gamma 0 and gamma j, club the gamma 0 with psi bar, and that will give me a change of sign, and dou psi bar over dou x j, what is left is gamma j minus m psi bar equal to 0. So, there is an overall minus sign, and what is there in the bracket is basically a total derivative, for derivative of psi bar dotted with gamma mu. So, this is nothing but I dou mu psi bar gamma mu minus m psi bar equal to 0, or I can write it as, taking away the minus sign, I dou mu psi bar gamma mu plus m psi bar equal to 0. So, this is what we will consider as the conjugate equation corresponding to the Dirac equation. So, now we have these two equations. One is the Dirac equation, I gamma mu dou mu psi minus m psi equal to 0, and I have dou mu psi bar gamma mu minus m psi bar, plus m psi bar equal to 0. First, multiply the first term with a gamma psi bar from the left. So, that will give me I psi bar gamma mu dou mu psi minus m psi bar psi equal to 0, and second term multiply by psi from the left, from the right, I dou mu psi bar gamma mu psi minus m, same term, plus m psi bar psi equal to 0. Okay. So, these together and these together. Add the second set. What do we get? I is there, you have a psi bar gamma mu dou mu psi plus dou mu psi bar gamma mu psi equal to 0. M psi bar psi cancels with minus m psi bar psi. Since gamma mu is a constant as far as the spatial coordinate and time coordinate is considered, the derivative will not act on that. So, we can actually write this as total derivative acting on psi bar gamma mu psi, the derivative acting on that. So, this is the divergence of psi bar gamma mu psi, which is equal to 0. So, we will define j mu as minus e psi bar gamma mu psi, and it is a divergenceless, or the derivative of divergence of j mu is equal to 0. This is basically the continuity equation dou by dou t rho plus divergence of j equal to 0 with j mu written as rho, the first 0th component, and j3 vector as the 1, 2, 3 components. And what is rho? Rho is nothing but minus e psi bar gamma 0 psi, and j is equal to minus e psi bar gamma vector psi. When I say gamma vector psi, meaning is that for each component of j, we have the corresponding component of gamma there. We added this minus e, like in the case of Klein-Gordon equation, to interpret it physically as the charge density, the rho, and the current density j. So, that is what we have here in the case of Dirac equation. Let us now consider a plane wave solution for the wave function. Psi can then be written as some u, which is a function of momentum, times e power I minus I p x, which has all the spatial dependence and time dependence in it. P denotes the momentum of the particle. Now, remember that we have a column vector with 4 components written in compact way as or represented in a compact simple psi, and on the right hand side u should also therefore be a column vector, or which it has 4 components, whereas the exponential is just some normal function. Now, let us look at the Dirac equation with this psi. When I take the derivative of psi with respect to x mu, that will bring out minus I p mu, and rest of it is psi. So, that will give you I gamma mu minus I p mu minus m psi equal to 0, or I can write this as gamma mu p mu minus m psi equal to 0. The I factors go away, or I could also write it as gamma mu p mu minus m acting on u equal to 0, because exponential I p dot x is anyway not equal to 0. So, that is easy. For short, I will denote this as p slash m u, a standard way of denoting gamma mu p mu is p slash. This is just a notation. Meaning is dot product of gamma mu with p mu. It is also equal to contravariant p and covariant gamma, the same. With this notation, we have the Dirac equation for the plane wave solutions as p slash minus m psi equal to 0. So, for free particles, we can actually consider this as the Dirac equation.